Excuse me. Hello, everyone. I'm Tracy Day, co-founder of the World Science Festival, and I'm delighted to welcome you all, both the audience here at Columbia University's Miller Theater and our online audience, to this special live-streamed event following the premiere of the fabulous PBS Nova miniseries, The Fabric of the Cosmos with Brian Greene. Thank you. Pardon me. Losing my voice. Thank you to our partners for tonight's event, PBS and Nova, and a special thanks to our host, Columbia University, for making this event happen. The World Science Festival is dedicated to bringing science to a general audience in new and exciting and creative ways. Pardon me. And sometimes the most exciting ways is to be able to speak to a renowned scientist directly, to ask questions. And that's what we'll be doing here tonight. One such scientist here on the stage, and two others who will join the conversation digitally. So I would like to introduce the scientist who will be joining us on stage, Brian Greene.
Thank you. So thank you very much. Thank you for coming. I'd like again to welcome the live audience and also the hundreds of millions of online viewers who are now joining us. And I especially want to thank those online viewers because I know that we are competing against the premiere of Top Chef Texas. We probably lost half our audience just now on that, but the rest of you, please do try to stay with us. So the point of this after-show event is really for you guys, the live and the digital audience, to drive the conversation, asking any questions that you'd like. There are a number of ways you can do that. Those of you who are at home, you can use Twitter, Facebook. You can also use a little box that's right next to the live stream feed on your computer screen. Those of you here, you also can tweet. We've got folks back there who will get it and they'll send it to one of these two screens in front of me. But you can also use the old-fashioned approach using one of these that are going to be circulating around. And I've been asked to tell you a little bit about microphone etiquette. Don't hold at the bottom because you'll block the signal. Hold at the top and apparently hold it very close to your mouth. And in that way it will all work. So let's just jump right in, and as the mics are going around, just raise your hand, and also you should stand up when you ask your question. So as you raise your hand, the mics will go around. I'm going to start with one of the digital questions as that's happening, and here is one from Twitter.
Not yet.
You spoke about the speed of light in the program, but what about neutrinos going faster than the speed of light? Well, that happened after the program was made. No, it's a great question because some of you may have heard there's this interesting recent result where neutrinos were sent from Geneva through the Earth's crust to Gran Sasso in Italy, 450-mile racetrack, if you will. And the thing is, the measurements seem to show that the neutrinos are reaching their destination 60 nanoseconds before they should. Namely, they're getting their 60 nanoseconds even before a beam of light would be able to travel that distance. Neutrinos seem to be going faster than the speed of light. And this would be a remarkable discovery, but this is a very difficult experiment. There are many, many uncertainties. Even the researchers who put forward this result know that there are uncertainties. You have to measure that distance precisely. You have to know exactly the length of time for that journey. The moon pulls on the Earth's crust, and that can slightly change distances. There are all sorts of complications. These are very smart people, so maybe all of these uncertainties have been taken into account. But I would bet everything I hold dear, well, almost everything I hold dear, that the result won't hold up to scrutiny. And I do say almost everything because there's a small chance that my two little kids may be watching online right now. So Alec and Sophia, I just want you to know, Daddy learned his lesson last time. I will not bet on you this time around, so you don't need to worry about that. But I should say that if the result turns out to be correct, it would be thrilling. I hope it's correct. This is what we live for, this kind of a revolution. I don't think this is one of those moments, but it could be. Okay, questions here. Anybody? I'm looking around for someone who has a mic. Anybody have a mic? Right there.
Not yet.
That's right. It's this old thing, right near the mouth. Good, good. There you go. Perfect. Thank you. I can.
So you were speaking about the fact that neutrinos being faster than photons is a trigger to you. Could you elaborate on that, on the meaning of what that means in case that is confirmed?
Yes.
And also, just 3 items I would like to offer. Neutrinos is the first one. Quantum entanglement is the second. And the third, UFOs. Thank you.
I wasn't sure if those last few were just a list or questions, but for the first question you asked, what could it mean if neutrinos did go faster than the speed of light, if special relativity, this idea that Einstein gave us, was wrong? Well, first it's useful to know why it is that we think that neutrinos wouldn't go faster than the speed of light. Well, Einstein's theory shows that as an object is moving, the faster it goes, the more mass, the more energy it has. The more mass means that it's harder to push it even further. So if a neutrino is approaching the speed of light, it gets heavier and heavier, needs an ever stronger push, and his math seems to show that if the neutrino went right to the speed of light, you need an infinite push to make it go faster still, and an infinite push isn't something that can happen. And that's why we don't think this is a correct result. If it is, well, we'd have to rethink a lot of our basic understanding of relativity. The most naive interpretation of the result would suggest that you might be able to send a signal to the past. So if something can go faster than the speed of light, if I have a neutrino gun and I fire it at you, the neutrino, in some way of thinking about it, would hit you before I pull the trigger. And that is so weird, that's so bizarre, that we really would need independent confirmation of those results to believe them. And people are undertaking experiments in the next few months, so we'll see whether independent experiments do confirm this result. I don't think they will, but I hope that I'm wrong. Okay, what have we got on the digital feed? What about...
Unless it's above the frequencies.
Oh, the entanglement and the UFOs. I hope I could get away without having to address those, but I see that we have a nice aggressive audience, which I appreciate fully. So entanglement, I'm going to defer entanglement to November 16th, when I hope you'll tune in to episode 3 of Fabric of the Cosmos, for all of you at home, where the focus is on quantum mechanics, and one of the main things we talk about there is quantum entanglement. For UFOs, I'm going to defer that to episode 4697 of Fabric of the Cosmos. That will air in the 25th century, so just stick around for that then. Okay, so back to the, so we have a Facebook feed. What about little black holes that might be created at CERN? What's up with that? Well, that is an interesting possibility. Some of you may have actually heard about this back in 2008 when the Large Hadron Collider was about to turn on. I got an enormous number of phone calls from like every news outlet to talk about the turning on of this machine. I was like, wow, has the world woken up to physics? It was really impressive, but it wasn't that. What it really was, there was this possibility that had been raised that at the Large Hadron Collider, in these energetic collisions, little microscopic black holes might be formed, and it was suggested that if they did, a black hole might be able to, say, suck in its surroundings, which means it would like suck in Geneva. Now, when it was just Geneva, people were like, okay, it sucks in Geneva. But then, you know, it could suck in the rest of Europe, and then it spills to America. Oh, then we start to worry about it. Is this something that's really possible? And it is something which, at least in principle, is worth thinking about. But when you do the calculations, you can show pretty convincingly that this possibility is so absolutely minuscule that if you worried about it, you should worry about walking outside and some huge dragon spontaneously forming and plucking you off the surface of the earth, because that's probably more likely. So this isn't a real worry after you do the calculations, but in fact it's a real opportunity. Because if these little microscopic black holes are formed, you can begin to study black holes in the laboratory. And indeed, this idea really comes from string theory that I and many others work on. And this would be a vital step forward in trying to make contact between the theory and experiment. So I see it as something that's quite exciting, not something that ultimately is dangerous. But again, we'll have to see what goes on. Questions here? Yes, go ahead.
Not yet.
Hi. So I was thinking about the neutrino
Unless it's
question,
above
and
the
I was
frequencies
wondering
that you can
whether
hear.
there's any way that instead of the Higgs field causing mass to accumulate with the with particles, is there something in space that could cause mass to get shaved off a neutrino?
So that the neutrino is actually lighter than you would think it would be? Go faster than you would have initially thought? It's an interesting thought. I don't know of anything that falls into that category. Our basic understanding of the fundamental particles that make up everything around us, and these more exotic particles that we don't see with the naked eye but we know are there, such as neutrinos, is as we describe in the program. If empty space was truly empty in the most pristine and naive version of that idea, these particles would all be massless. But what we think is the case is that it's not empty, as we describe in the program, that there is this kind of suffused form of energy that's all through space. It comes in a variety of forms, and the one most relevant to your question, as we described, comes from this Higgs field, and the particles are trying to burrow through. And as they try to burrow through that, they pick up mass. I don't know of a process by which that would be reversed. So, interesting thought, but I don't know of anything which would actually execute that idea. Okay, what else do we have coming in?
Not yet.
What is the speed of gravity? If you were to imagine our sun instantaneously disappeared, would we feel the effects on Earth immediately, or would we wait 8 minutes? That's from someone on Facebook. And the speed of gravity, interesting thought, isn't something we really discuss in the program, but I'm happy to address it. And the thought experiment that this person is suggesting is if you have the sun out there and the sun just disappears, well, we know that we'll still see the sun for about 8 minutes because that's how long it takes light from the sun to travel the intervening space and enter our eyes. It takes about 8 minutes. The question is, how long would it take us to feel the effect of the sun's disappearance?
Not yet.
And I suspect that this person doesn't mean sort of emotionally feeling it, I mean like physically feeling it, because if the sun goes away, our motion through space will change. How long will that take? And what we learned from Einstein is that it will take the same 8 minutes, because according to the general theory of relativity, the speed of gravity equals the speed of light. So if the sun were to disappear, we'd take 8 minutes before we'd notice it's gone, and it would take the same length of time before we'd feel it by an abrupt change in our orbit. So one and the same speed. So anytime you hear the speed of light, you can equally well interpret it as the speed of gravity. Other questions here?
Not yet.
Anybody? So you guys should try to get the mics over. We got somebody over there? Yeah, go ahead, please. Yeah.
Hi, I had a question concerning the applications of pure mathematics to physics.
Yes.
For example, per David Hilbert's quote, we must know, we will know. I want to ask whether you thought, if you or other members of the physics community thought that if there were to be a possible solution or proof of the Riemann hypothesis, would that potentially be automatically used to help solve some of these major problems?
It's not like we're in physics just waiting for that particular mathematics problem to be solved. There isn't, to my way of thinking about physics, some critical issue that relies upon a solution to that famous mathematical problem. The general question, of course, is what mathematics applies to the physical world, and what mathematics is just stuff that we have dreamed up, and it's interesting and worthy of pursuit, but doesn't have a physical associated phenomenon that mathematics describes. And that's a very hard question to answer. When it comes to string theory, some think that string theory may be just mathematics, that it may not apply to the real world. We don't know yet. Only experiment can tell us that. But I don't think that all mathematics necessarily applies to physics. I think there really is a subset of mathematics that's relevant, and it's up to us to figure out which mathematics is the right mathematics to describe the world around us. All right, so we have a Twitter question. What is the holographic principle, and what are the scientific and philosophical implications that follow from it? And that is a good question, and naturally actually allows me to bring Lenny Susskind, who is in the program. He's going to join us by Skype. That's actually a better question for him to answer than it is for me. So let's bring Lenny Susskind into the conversation. And in the program, he was the gentleman with the beard who speaks with a wonderful Bronx accent, one of my favorite physicists. He's a professor at Stanford. He's the Felix Bloch Professor of Theoretical Physics at Stanford. He's one of the discoverers of string theory, and he's really widely recognized as one of the most important physicists of our age. So I'm thrilled that he's in the program, and it's great that he will be joining us by Skype. And there he is. Hi, Lenny. How are you doing?
Hi, Brian. How are you?
Good, good. Thank you. So let me actually begin with not the question that was asked. We'll come back to it because there's another one that I see here that's relevant too, which I think is a nice lead-in. The questioner from Twitter says that they read somewhere that you really wanted to be a plumber, but when that didn't work out, being a physicist was your fallback. The question is that right?
Yeah, that's right. I didn't want to be a plumber, no. I wanted not to be a plumber, but I had to be a plumber. My father was a plumber, his father was a plumber, and I had to go to work as a plumber. I didn't have any choice. But I managed also to go to college for a little bit and learn some physics, and suddenly discovered I wanted to be a physicist. I didn't want to be a plumber. So there's some truth to the story. But the story that I wanted to be a plumber is untrue. I hated being a plumber.
Well, thank you for clarifying that. So let me start with one of my own questions, and then we'll go to some of the others that people have. So I don't know if you have yet seen the program because it hasn't aired in California yet. I don't know if you saw it earlier, but one thing the program does not cover is the interesting battle that you had with Stephen Hawking about the issue of if something falls into a black hole, where does the information that object contains go? So Hawking thought it would disappear, you didn't. We basically in the program just go from the result that it doesn't disappear, but perhaps you can fill in a little bit of the background there.
Well, yes. I mean, Stephen very sensibly raised the question, what happens to information when it falls into a black hole? Now, it is a really, really deep principle of physics. It's so deep that we even almost forget about it when we state what the principles of physics are. A very deep principle of physics that information means distinctions between a proton and an electron is a bit of information. The distinction between a male and a female is a bit of information. What it would mean for information to disappear is that distinctions which existed to begin with somehow disappear in the system, and you can't ever, under any circumstances, recover those distinctions. That's a very famous principle in computer science, that distinctions can't disappear. A bit of information which you erase from your computer doesn't really disappear. What happens to it is it goes out into the atmosphere, and it jiggles around among all the atoms, all of the molecules, and so forth. But if you had the power to be able to study every single molecule in the room, you could recover that little bit of information. On the other hand, Stephen said, wait a minute, stuff falls into a black hole. If it falls into a black hole, it's really gone. Besides which, black holes eventually evaporate. If they evaporate and things fell into them, where did they go? They're gone. The evaporation means the black hole disappeared. It's not in a black hole. On the other hand, it could not have gotten out of a black hole. The answer, which I'm not sure, I think Stephen sort of partly knew, but the answer is the information never really does fall through the horizon. It gets plastered onto the horizon, it gets spread over the horizon, it gets what we call sometimes scrambled over the horizon, and then the horizon evaporates and it comes back out into the what's called the Hawking radiation. The Hawking radiation is the evaporation products, very much like a little bit of information, a little bit of ink falling into a puddle of water. And eventually the puddle of water dries up. What happened to that little bit of information that was in the ink? Well, it goes off into the evaporation products. The difference was that there was real good reason to believe that once something falls behind the horizon of a black hole, it really can never get out. It would have to exceed the speed of light to get out. And so there was a puzzle there. The answer was a complicated answer and a very subtle answer. It turned out that the question of where a bit of information is it here or is it there, is not a precise question. It is not a question that we can always answer unambiguously. And the way that it turned out is the question was very similar to asking, if you look at a hologram, is the information about the hologram the piece of film, which has all of these squishy, scratchy little marks over it, or is it the image? Well, it's both. The information that's in a hologram is both the information in the squishy, scratchy piece of film, and it's also the information in the reconstructed image. So what falls behind a black hole is kind of like the image of a hologram. The surface of the hologram, or the film, is more like the horizon of the black hole. And yes, the black hole does evaporate, and the result is that it's as if the film evaporated, and when the film evaporated, that information goes off into the atmosphere, and the image just disappears. Did that help?
Yeah, no, it does. So if I paraphrase the question that was sent in,
Yeah.
what is the holographic principle? And I guess the follow-up question I might add, just for clarity, is all that we're talking about has to do with black holes. How do you make the leap from a conclusion that seems very tied to the physics of black holes to a conclusion that we might want to apply more generally even to the space that we're living in right now?
Well, I can tell you, yeah, I mean, leaps are something that you can never really reconstruct how they happened. What happened in your brain that suddenly made a leap, I can't explain what happened. But I can tell you some things. First of all, anything that could be outside a black hole could also be inside a black hole. A whole civilization, a whole solar system, the whole works. If a black hole was big enough, it could contain all of that. So on the one hand, there's no limitation on what can be inside a black hole. Anything could be inside a black hole. If the black hole is big enough, then that anything, the civilization, the solar system, and all of it, has to be also described by these little bits of information that get plastered onto the horizon of the black hole. But when I was thinking about it, this was sometime around 1993, 1994. Gerard 't Hooft was also thinking a lot about it. We were thinking also partially about cosmology. Now, I was somebody who tended to believe that there was a cosmological constant in nature and that the universe was expanding or accelerated expansion. And if it is accelerated expansion, the universe is described by something that's called de Sitter space. De Sitter space is a very interesting thing. It's almost like an inside-out black hole. We are in the inside, and out at a certain distance away, 15, 20 billion light years away, there's a horizon. And things fall out. They don't fall into the black hole. They fall out from our universe, out through that horizon. It's like an inside-out black hole, but don't get the idea that it means that we're inside a black hole. It doesn't. It means that the universe itself is, as I said, like an inside-out black hole, and things fall out through the horizon. I began to think, wait a minute, there's something going on here. what if the horizon of de Sitter space is similar to the horizon of a black hole? And mathematically it is. Mathematically it's almost identical. Then that must mean that everything that's on the inside of the universe must be describable as a hologram or a kind of film on the surface way out there at the horizon of de Sitter space. That's the way I was thinking about it. Gerard was thinking about it a little bit different. But together we came together with this notion that everything within a region of space can be described as if it was surrounded by a film where that film was like a hologram. Nobody really took this too seriously at first. I took it seriously, but nobody really took it seriously except for a very handful of people. Ed Witten was one of them. Juan Maldacena was one of them. The reason it really became consensus science was because a very, very particular kind of space-time, anti-de Sitter space. Don't worry about what it means exactly. It wasn't the space that was discovered by de Sitter's aunt. It's another kind of space. Anti-de Sitter space has the property that it has a kind of boundary. And it's a very special space with an enormous amount of symmetry, very amenable to mathematical analysis. String theory had a lot to say about it. And by the time Juan Maldacena got his hands on it, he was able to prove very, very rigorously that this holographic idea was correct within that context. Once that happened, everybody jumped and said, oh, this holographic idea must be right. And that's the status of it now.
So when you walk around, do you actually have in mind that you truly may be, in some sense, this holographic projection of laws that exist on this distant bounding surface? When you go to the store, is that in your way of thinking about how you go around everyday life?
Yeah, that's why I trip over my feet so much. You know the answer to that. Of course not. This is one of these things which is so bizarre and so peculiar that if your mind was wired to be able to really grapple with it and understand it in the deepest possible sense, you'd probably be dead because you would have tripped over your feet or walked into a wall. No, I don't. I'm a normal human being. I don't think holographically.
So let me ask just one final question, which also comes in. What's your guess? Will the holographic principle one day be viewed on par with the equivalence principle or the principle of complementarity? Do you see it as ranking in that spectrum of contributions?
Oh, I thought it already was.
Yeah.
I think it's almost the case that it is. I know very few theoretical physicists who I really think of as serious theoretical physicists that don't take it seriously. I think it's already reached consensus. I'll tell you what the difference is. The difference is that the kind of experiments that you would have to do to confirm it are so difficult and so way out there beyond the range of our technology. Getting close enough to a black hole to be able to see the Hawking radiation from it, cooling the black hole to the point of view where it does radiate, all the sorts of things that you would need to do to turn this into experimental science are not fundamentally impossible, but they are way beyond the range of our technology. And they'll probably always be beyond the range of our technology. So it's not clear to me how it will ever become experimental science, and I think that's very important. But as far as theoretical science, as far as theoretical physics goes, I think it has already achieved the level of being a basic principle, and I don't think that's going to go away.
Well, great. Well, thank you, Lenny, for joining us, and thank you for being in the programs. You can see Lenny in the other programs as well. Leonard Susskind, thank you. Appreciate it. All right, so a couple of other questions that come in. One from Twitter is actually a follow-up to the one that was asked before over there. Do you think mathematics was invented by humans to understand the universe, or is the cosmos inherently mathematical? It's sort of a version of the question that was asked before, but maybe I should give a more full answer to that then. My feeling is that math has proven itself a vital tool for understanding the universe, at least the attempts that we have made to understand the universe. Does that mean it is profoundly interwoven with reality, or is merely a description that the human mind imposes upon it? I'm not sure, and I'd even go further. I could imagine that one day, speaking of the UFO question, one day maybe we encounter aliens, just hypothetical aliens, and we start to talk to them, and they say, show us how you've been going about trying to understand the universe, and we break out our mathematical theories and so forth, and the aliens look at it and they say, oh, mathematics. We tried that for a while too, but the real way to understand it is this, and then they would show us some other approach. The problem is, if any of you on Twitter or Facebook or in this room ask me what would it be that they would show us, I don't even know how to frame it in a way that ultimately it isn't like mathematics or is mathematics or is isomorphic to mathematics. So I have trouble going that final step, even though in principle I can imagine that math is ultimately not the right language. But I can't even imagine what the right language would be if indeed that were the case. Questions here in the hall. Anybody has a mic? Yes, sir.
Two more questions about the holographic universe. First of all, when I saw the wallet falling into the black hole, I thought, well, it sounds kind of a lot like the transporter from Star Trek, where they take matter and they convert all of it into information, but it would end up being such an insane amount of information that it's probably never going to be possible. So it's like the amount of information on the surface of every black hole out there nearly infinite. And the second question I have is from a concept that I didn't quite fully understand from the Elegant Universe. It's about Calabi-Yau structures and how two different spaces on either side of one can be basically of two different geometries, but have, you know, you could experience the universe in the same way in either one.
Oh, you're talking Elegant Universe, the book, not the TV show.
Right.
Yes, okay.
And do you think that idea, this idea that you could have two different geometries, but the same universe, if that's related to the holographic universe principle?
Well, so for the first question, you're asking how much information is there on the outside of a black hole? So in the program, we showed these zeros and ones that were splattered on the outside, the horizon of a black hole. How much information is there? It's not infinite. We can actually give you a precise mathematical number, a means for calculating how much information there is on the surface of a black hole. Here's what you do. You take the area of the surface and you divide it by 4 times Newton's constant. That's a number, and that number gives you the amount of information, the number of bits, the number of zeros and ones that can be stored on the surface of that black hole. If you're familiar with these ideas, it's if you take the surface area of the black hole and you break it up into little grids, each of which has this area of a Planck length on each side, so a Planck squared length, or actually 4 times a Planck length squared. And each of those area elements can hold one piece of information, a 1 or a 0. And that's the amount of information that's on the outside. Now the second question having to do with Calabi-Yau shapes and this idea of two different shapes that can give rise to the same physics. Mirror symmetry, I'm fond of that. That was one of the contributions that Ronan Plesser and I started way back in 1990, so that is close to my heart, but I don't see a connection between that and any of the holographic ideas. At least I don't see any connection yet. So who knows, maybe sometime, but certainly not yet at all. Okay, one more question there. Yes, sir.
My question is about the state of the string theory as it in current experimentations at the LHC.
Yes.
Whether it's been something that has confirmed or disproved it.
So yes, the state of experimentally testing string theory. Other questions that people might want to discuss here? No, it's a very important question. That was flippant, I don't mean it. It's the only way that we'll ever determine whether this theory is right or wrong. And as of now, from the LHC, there hasn't been any real breakthrough at all. So far, we haven't seen the Higgs particle. And so sort of thankfully this film came out now and not 6 months from now, because it could be the case. The window of opportunity for the Higgs field is getting smaller and smaller every day. as the data is coming in. Now again, if we don't find the Higgs, that will be exciting. It won't be something where we're sad and depressed. We'll be like, okay, now we have to go back to the drawing board. This 30-year-old idea, or even longer, back from 64, we have to try to come up with something else. And there are other ideas that people have developed. String theory, too. Is it possible that we could get insight into string theory from the Large Hadron Collider? It is possible. I consider them all long-shot possibilities. We could find evidence for extra dimensions through the powerful collisions of particles, creating debris that flies out of our part of space and goes into the other dimensions. That's one way that we might find evidence. Another way would be to find a class of particles called supersymmetric particles. These are particles that the theory says should be there, but yet we haven't seen them, and the belief is that they're heavier than their known particles in the world around us, and that's why you need the Large Hadron Collider to create them in powerful collisions. But as yet we haven't seen any evidence in the Large Hadron Collider for the possibility that string theory is correct. And in fact, there is another question here which has a slightly different flavor, but it's sort of the same. So far, somebody from Facebook says, so far there don't seem to be any breakthroughs coming out of CERN. If they close the door on the Higgs and supersymmetry, which is a key part of string theory, will you think your life has been a waste? I never thought of it that way. But yeah, I guess. No, I wouldn't, because look, what is science about? Science is about every generation has a group of individuals, scientists, who are willing to press into the unknown to try to figure out deeper understanding of how things work. And sometimes you're going to find things that are right, and sometimes you're going to come upon ideas that are wrong. And our generation faces the following challenge, which is the previous generations have been so successful. Lenny has been so successful in helping to develop ideas that can describe electrons and quarks and W bosons and gluons with such fantastic accuracy that we have been propelled to take on even more difficult questions, like how to put gravity and quantum mechanics together, questions that are very difficult to test with experiments. So we are sailing through the darkness without the bright light of experiment to guide us. And that might mean that we're going down a vastly wrong trajectory. So who knows? Alrighty, so back to the feed here. Here's a good one. How reliable is the data for an accelerating, expanding universe? Would you risk your paycheck on the reliability being maintained over the next 10 years? And there's somebody else who perhaps would be better to answer that question because his paycheck is perhaps more directly tied to it, and that is Saul Perlmutter, who will join us also by Skype. So you also saw Saul in the program. He was the guy with this wonderfully messy office who was talking about this discovery of dark energy. He's a professor at Berkeley in the Department of Physics, a senior scientist at Lawrence Berkeley National Laboratory, the leader of the Supernova Cosmology Project, and the winner of the 2011 Nobel Prize in Physics. So please join Saul Perlmutter. So quickly, Saul, just one question I wanted to ask you. The phone rings, it's 3 o'clock in the morning. Did you think it was the Nobel Committee?
Well, actually, I thought it was the morning, and I picked up the phone, and they said, this is a reporter calling from Sweden. How do you feel? And I said, how do I feel about what? Because the committee hadn't reached me yet. It took them 45 minutes.
Very good, very good. Well, so the question was asked. So we just saw in the program this fantastically interesting result that the universe is expanding ever more quickly, and this explanation that there must be this dark energy that's pushing everything apart. The question is, how reliable is this result? Do you feel that there's a chance that 10 years from now we might look back and say, oh, got a little something wrong and we have to retract this way of thinking about things?
Well, let me answer it in two parts. If you ask about the data itself, the supernova results have just been getting stronger and stronger. We did it with the original measurements had some 50 supernova between two teams in it, and by now there's 10 times as many supernova, and they're much better measured, and that result looks very strong. And then also there's been now a number of other techniques that we've used to triangulate on the same basic answer. And so if the supernova data were to just go away, we would still have very strong evidence that we're seeing this odd effect. On the other hand, it's also true that we can't say for sure that the right way to describe the effect is an accelerating universe until we actually understand the full picture of what's going on. And so there are some crazy versions of the theory in which there's other ways in which you see the same basic effect, but it's still a fascinating, mysterious effect nonetheless.
So what's your guess right now for what is the origin of the effect? So there's a question, I'm just going to paraphrase it. Basically, we call it dark energy, but the question is that just a word that is trying to obscure our ignorance, or does it really tell us something about the universe?
No, in my current picture, I would say it's just a description of our ignorance at this stage. There's so many different theories. There's so many different ways you might explain what's going on. And I think it's fair to say that if you ask the thousands of theorists who proposed these theories, if they would stand behind theirs as the right explanation, I think almost any one of them would say that no, they're just trying to expand the range of possibility. And then they turn back to us, the observers, the experimentalists, to try to give them a little bit more of a pointer, some more data that will narrow in the range of what the answers might be. So from my perspective, I'm wide open. I hear many theories that sound wonderful. Some of them are just more fun than others, but I think I'm completely ready to find that the data points us in any of those directions.
So the simplest explanation seems to be this one that goes back to Einstein, that there might be the so-called cosmological constant, as we describe in the program, which roughly is this intrinsic property of space that gives it a kind of intrinsic elasticity, which through the wonders of general relativity gives rise to anti-gravity, repulsive gravity. Do you think that is where the data is pointing?
Well, all the data is completely consistent with that result today. But it's also true that almost any theory right now will still satisfy what we see in the current data. And so people are, I think, tending to look at this Einstein's cosmological constant as the simplest theory, partly because it's the one that they've known about for longest. And from my point of view, given that we have no good way at the moment to explain why the value is so much lower than what the theorists would have predicted, I think they might have guessed something that was 10 to the 120 times bigger. Given that that's the case, I put it still in the category of the many possibilities that could very well turn out to be right and that we really have to explore, we have to try and get to the bottom of. I should also point out that the one other time that the universe apparently we think did accelerate was during the inflationary period, just that first tiny fraction of a second after what we call the Big Bang. And for all we know, this is another one of those fields as caused that acceleration. And it may also decay away again in the future, in which case it would not be Einstein's cosmological constant.
So then what is on the horizon to try to figure it out?
Well, in the last 10 years or so, we've actually made a lot of progress in trying to develop a number of different techniques. So first of all, we've pushed the supernova much, much harder, and we've gotten to the point where we could make a much more precise measurement using the supernova, even than we've done today. We've also developed a couple of other techniques, taking advantage of things we know about the distances between the hot and cold spots in the early cosmic microwave background, that glow left over from the Big Bang. And these different techniques, I think, should allow us to triangulate in on at least a region of the theories. And I'm hoping that if we did that, and I'm fairly optimistic that we have a good chance of doing that in this next decade, that the theorists then will have an aha moment when they see, oh, okay, if it's in this region, I think I know what's going on.
Right. Well, that would be exciting if we could figure it out. I mean, many people say that the dark energy is the biggest mystery that we face. Is that your characterization of it as well?
I mean, it certainly, right at the moment, it feels like one of the ones that's just hitting us in the face with 3/4 of the stuff of the universe that we don't know about potentially. And obviously that's the sort of thing that we really should get to the bottom of. Personally, I'm kind of optimistic. I think that every time we get more data in these early stages of our understanding of cosmology, we've learned a lot more. So I'm betting that if we get one more big shot of data coming up in this next round of experiments, I'm betting that we'll have at least a fighting chance at this.
Well, that would be great. Saul, thank you so much for joining us. Everybody, please thank Saul Perlmutter. Have a good time out there in Sweden. Fantastic.
Thank you.
So let me just ask we still have a little bit of time here. So here's one actually about the show itself, which says that often people say when seeing a movie made from a book that the book is better than the movie. Since you are involved in both, you are in a unique position to judge. What's your perspective in this particular case? Well, that's kind of a hard question. I think that a book and a movie in this case are vastly different beasts, right? I mean, in a book you can go into greater detail. You assume that people can flip back, they can mull over an argument, whereas a television show, you really want it to communicate in one shot. Maybe the people who worked on the film, which we have right here, any of you guys, Jonathan, Joe, Paula, any perspective on that?
Well,
Can you turn Joe's mic on?
Can you hear me?
Yes, I can.
We're a little biased, I guess, on this point, but no, I think they serve kind of somewhat different purposes. I mean, I would hope people would watch the show and then be interested in turning to the book to find out more. But,
yes, that would be good, especially in hardcover, please. Yes, thank you very much.
And buy the DVD, of course.
Right. It's also perhaps worth saying, as we were developing the film and discussing the script, there are many times where I think it's accurate to say there's kind of a tension where I wanted to go a little bit deeper into the ideas, and the team felt that was probably too much for something that would work in a television context. And I should say that they were always right, and I do mean that without being facetious. Oftentimes they would give me the opportunity to do a longer version, a more complex version of some of the ideas, and then we'd look at it and it just wouldn't work. So there really is a difference between the two, and I think you guys did a fantastic job of reining in the material in a way that communicates but is still not watering down the ideas. So anyway, that's my perspective on that. Thank you. A couple more questions here. Who has the mic? Whoever has the mic, I don't see it, just stand up, start to talk. Go ahead, please. You got to have the mic. Yes, thank you. Oh, yes.
Could you explain string theory briefly and simply?
Yes, I can.
Please?
Yes, I
Thank
can.
you.
I can do that. Oh, you want me to actually do it? So the idea of string theory is that the basic constituents of matter might not be what we long thought. So the old idea, which is still perfectly viable, it may be the right idea, is that there are certain collections of particles that make up everything. So you know about these particles. You have atoms that are made of protons and neutrons. You've got electrons going around. Inside the protons and neutrons, do you know what those particles are? Quarks, yes. Thank you very much. So very good. Actually, can you simply tell us what string theory is? So the idea is that you have electrons and quarks and a few other exotic species of particles. We've discussed neutrinos. But all of these particles in the conventional description are little tiny dots with no further machinery, no further particles, no further substructure to be found inside. And the basic idea of string theory is that that idea might be wrong, that there might be another layer to the story, that inside electrons and quarks and neutrinos and every other kind of particle would be a little tiny filament. It's a little filament of energy. It kind of looks like a string, and that's why it's called string theory. And the basic idea is that these little filaments of energy, these little strings, they can vibrate in different patterns. Now you know when you have a cello and you pluck strings that vibrate in different patterns, they produce different musical notes. The idea of string theory is that when the strings vibrate in different patterns, they don't produce different musical notes, they produce different kinds of particles. So an electron would be a string vibrating in one pattern, like a C sharp. A quark would be a string vibrating in a different pattern, A flat, just to use the analogy. So the basic idea is that all the matter in the universe, arises from the different kinds of vibrations of this hypothetical entity called the string. Now you might say, well, okay, that sounds like a reasonable idea. Why hasn't it been tested? Why is it so hypothetical? And the reason why it's hypothetical is because these little strings, according to the conventional description, are really, really tiny. About 10 to the minus 35 meters long, decimal point 34 zeros and a 1. And that's so fantastically small that it's even hard to wrap your brain around. If I'll give you one quick analogy just to set the scale, if you took an atom and magnified it to be as big as the observable universe, huge scale of magnification, then the little string under that same scale of magnification would be roughly the size of a tree. So a tree is to the observable universe as a string is to an atom. And that just makes it a huge challenge to try to see these little strings. But we hope that through indirect means we may one day be able to do that. But we have not been able to do it yet. That may mean the theory is wrong, or it may mean that we just haven't been able to get far enough along in our technology to test these ideas. You're welcome. Other questions? Who has the mic? Go ahead. If you have the mic, yes, go.
Hi. So I'm actually a student here, and so this question is from the perspective of somebody thinking about going to science. So I saw in the show that it's a collection of theories and everything over the past century or more, and it's all these grand ideas, and they're very exciting, and I love to see them. But then on a more day-to-day basis, when you go into work, for example, I'm sure you're looking at equations every day, and when I'm looking at a physics equation, it's less exciting. So I'm wondering, like, on your level of science, of physics, when you're at work every day looking at equations, do you feel that level, that thrill, sort of that a lot of the sort of lay people feel when they're watching the show and seeing these grand theories on display?
Always. Absolutely always. No, you're right. I think physics is like any other field. There are these wondrous moments when something spectacular happens, but there are long stretches where it's just a long haul. It's a lot of work to try to make progress. Every result that you have in physics typically relies upon a tremendous amount of those mathematical calculations, right? Everything that you saw in these programs, even if it was described in words and shown in animation, there's this whole body of mathematics that you are alluding to that underlies it all. And the idea is that if you're going to go into a field of this sort, you have to enjoy the process as much as you enjoy the great breakthroughs. Because if you're living for the great breakthroughs, you're bound to be disappointed because they're few and far between. I mean, even Einstein, right? Einstein spent 10 years trying to work out the general theory of relativity that we described, the pool table, the bending, and so forth. That represented 10 years of work. And later in his life, when he reflected back on those 10 years, he described it as years of anxious searching in the dark for a truth he could sense but could not quite see until finally he emerged from the darkness into the light. But that was 10 years. Most of us would not be able to sustain work on a single problem of that sort for 10 years. And that's really what distinguished Einstein. But indeed, you don't have the thrilling moments, one after another. Rather, you have to be fired up by the process and the possibility that one day the process leads to some big breakthrough. So I think we have time for one more question here. Yeah, go ahead.
Mr. Greene. I think it was Sir Isaac Newton who famously said that if I have seen further than the rest, it is because I stood on the shoulders of giants. Which shoulders do you stand on? To whom do you owe an intellectual debt? And if to anyone, how do you move beyond the ideas of your intellectual predecessors?
Well, we all stand on the shoulders of the people that were described in the program. So certainly the giants of physics that have set the framework, are Newton, and we didn't talk about Faraday, but Maxwell for electromagnetism, Einstein for the general theory of relativity, and then the whole spectrum of people that worked on quantum mechanics, from Bohr and Heisenberg and Schrodinger and Pauli. All of these individuals propelled our understanding vastly forward, and we are standing on their shoulders. And the hope is that our generation is scaling the mountain of explanation a little bit higher, allowing those that come after us to perhaps stand further and see further than we've been able to. But we don't know. And that is something that only time will tell. So I have here a bunch of questions that are coming in, and I'm told that we don't have much time, so I should give very quick answers to these. So I'm just going to race through. Hopefully some of them are interesting. Are you guys just making all this stuff up? Yes, of course. I drill a hole at the North Pole all the way down to the South Pole. I drop a brick down it. What happens to the brick? Let's ignore friction from air. Boing, boing is where that question comes from. The answer is that the brick will oscillate up and down through that tunnel through the earth. And if I remember correctly, the period will be about 85 minutes, 42 and a half minutes up, 42 and a half minutes down. A century from now, how do you think the future scientists will regard the last 25 years of physics? Sort of the same question. I don't know. I hope it's not viewed as a period where we were misled by our mathematics, but only that will be clear at that point. Is there a parallel universe where you are Brian Austin Greene? I certainly hope so, because otherwise we have to throw away all our theories if that's not the case. How does understanding the universe make anyone's life better? Well, I think that the ability to understand how things work, to be able to see beyond the surface level of reality and understand what's happening deep down, to me, frankly, it's what makes life living. So I think that is a vital thing to a rich and full life. Given the option, would you travel to the future or the past? I would travel to the future. I can always read about the past. Why isn't more research done on glial cells, since they are more prevalent in the brain than any other cell? I have no fucking idea. If this universe is a block where time is just another spatial dimension, what accounts for the direction of time? Tune in next week. We do talk about that. What causes inertia? A big Chinese meal? I don't know. Maybe it's the Higgs field. I don't know. Is quantum entanglement real? Again, the quantum program, November 16th. What do you think of consciousness? I'm for it. Absolutely. I like it. When are you going to run for president? As soon as anyone convinces Lady Gaga to be my running mate. Okay, so thank you very much. Again, I should say, thank you. So one quick thing on the way out. Many people ask questions. I only got to a fraction of them. I'm going to try to answer a few questions a day for the next month. Go to the World Science Festival website, and I hope that the questions you ask will be answered. Again, thank you very much.